Hello everyone. In today's video I want to take a look at the second way to multiply vectors called the cross product. Again, it gets its name from the symbol that we're going to use to try and distinguish between the two ways that we multiply. Cross product is also referred to as our vector product because in this case we will get a vector as a result. And if you remember, the dot product gave us a scalar as a result. Few points here. This will only work in 3 space. It does not work with 2-dimensional vectors. You'll see why as we look at what this actually means. The cross product of u and v will produce a vector that is perpendicular to both u and v. So if we look at u and v as 3-dimensional vectors in 3 space, basically what we are going to get is when we do the cross product, it will produce a vector. So here will be our vector u cross v. And that vector will actually be perpendicular to both this vector and this vector here. So I'm going to put some right angle markers in here. And again, you got to try to picture that that's in 3 space so that these here two vectors, when I do their cross product, will produce a vector that's perpendicular to both of those. And then lastly, this will follow what we call a right-handed system, which means if I do u cross v, some of you who are taking physics will have seen this idea when you're dealing with electricity. It means that if I point my fingers in the direction of u and then I wrap them towards v, my thumb will point in the direction of u cross v. Which does bring up an interesting point, and that is if I reverse the order here, we actually get a slightly different vector, because if I point my fingers at v and then wrap them towards u, my thumb is actually pointing in the opposite direction. So in this case, the operation is not commutative, because it actually produces a different answer. So if I cross these vectors in the other order, I will get this vector here, v cross u. So that's its geometric interpretation. That's what we're actually finding. How do we calculate this? I'm going to skip a proof here. I will tell you that if you want the proof, you can go to the textbook on page 181. It is quite long, so I won't include it as part of the video here, but I'll simply give you what the formula is to calculate this. So if I want to do the cross product between u and v, then here it is. And if you look at the formula, it's actually quite long and has quite a bit of calculation here. There are 3 components for this vector. Here they are, and how we calculate them. So the first one alone is a2 times b3 minus a3 times b2. And the question then would be, well, how do we remember what's getting multiplied together and what's getting subtracted here as we try to form this vector? So here's how I do it. There's a few different strategies that you can use, but instead of trying to memorize this pattern here, what I would do is this. Whenever I want to calculate the cross product, I'm just going to stack the 2 vectors one on top of the other in the order that I want to do the cross product. So u on top of v, since u came first here. And basically what I'm going to do is whenever I want to calculate one of these components, so for instance, if I want to calculate the first component, what I'm going to do is cover the component you want to find and start at the next position. So if I want to calculate the first component, I'm going to take these 2 vectors and I'm going to cover that first component. And essentially what we're going to do then is just cross multiply here. Interesting that we call it the cross product and that this ends up being a cross here as we do this as well. And I will cross here to multiply, and then I will subtract the 2 answers that I get. And if you notice, that'll give us our first component here, a2 times b3. There it is, subtracting a3 times b2. So usually I just draw some arrows in here to show that that's what we're going to do. So if I want the first component, I cover the first component and I cross the remaining 2 components. If I want the middle component, well, I'm kind of stuck because now what do I cross that with? Normally what we would do then is I take these first components just to make this easy and I just rewrite those on the end. So if I want to now cross, to get the middle one, I would do a3 times b1, okay, on the one diagonal, and I would subtract off the other diagonal. So A3, B1, there it is. Subtract off A1, B3, there it is. And then lastly, if I want to find the third component, I would just cover the third component, and I go back to the beginning, and I will cross these two here. So A1 multiplied with B2, and I will subtract off A2 multiplied with B1. Okay, so let's put that into practice. We'll do an example here. Just asking you to find the cross product. So if we do that, A cross B, so you can see what this looks like. Again, over on the side, I'm just going to write these two vectors. I'm just going to stack them one on top of the other. So there's my one vector, my other vector, then 6, -5, and 3. Because we saw that we're going to have that first component at the end, I often do this just right away. Say, okay, I'm just taking the first two components and rewriting them at the end. So as I start doing my cross product here, what I'm going to do is cover up the first component, and then I just cross these two here. So if I do that, I end up with 6 take away -15. Now you do have to be careful with your integers. 6 take away -15, same as 6 plus 15, gives us 21. Cover up the next one, and I cross then here again. I'll try to keep the same coloring I did up above. So if I do this, I'm going to have 18, and I'm going to subtract 3. 18 subtract 3 will give us then 15 for that second component. Cover up the last one, and I cross again. Here I'm going to get -5, subtract 12, which will give us then -17. And there's our cross product. In the second example, similar question, although I haven't officially asked you for a cross product, but this is the whole purpose behind cross product, is that it will produce a vector that is perpendicular to two vectors. So when you see something that says, well, we want to find two vectors that are perpendicular to, and it is perpendicular to two separate vectors, vector A and vector B. If I want to produce a vector perpendicular to two vectors, then I'm going to use this idea of a cross product. So if I want then here, I can say, well, A cross B equals, and again, same idea. I'm just going to come to the side and write those two vectors, preferably in component form, as it's much easier to see as we do our cross product. I'm going to take those first components and rewrite them on the end. Okay, and then I just start covering up and then crossing those multiplications here. So if I cover up the first one, I'm going to have -12 subtract -42. Again, careful with your integers. That'll give us 30. Cover up the next one. I'm going to get 7 subtract 9. That'll give us -2. And then cover up the last one and cross. I'm going to have 18 subtract 4, which will give us 14. So there is a vector that is perpendicular to both of these. Now notice in this question though, I've asked you for two vectors. So here's the catch. Any multiple of this vector, so any multiple of A cross B, would also be perpendicular. If I go back to the diagram, keep in mind what we have found is, say, this vector here. If I want another vector that's perpendicular, I can take any multiple of that vector. So if I was to take this vector and multiply it by 2, it still remains perpendicular. If I want to multiply it by 10, it would be significantly larger. That would still be perpendicular. I could actually reduce it. I can make it half as big, or I can make it a quarter as big. We could also multiply this vector by a negative, and if I multiply it by a negative, it's going to change its direction. In other words, we'd get this vector down here. So really any multiple of this vector that we found will also be perpendicular to both of these. Now, the importance of this is not only that we can find many vectors that are perpendicular, but often when we do our cross product, we'll get results that are not reduced. So if we want a second option, what we could do is this here. We often reduce our vectors. We want perpendicular ones, so often reduce. So what I'm going to do for my second answer is just take this one and multiply it by a half, and that will just reduce all my numbers here like reducing fractions. So I'd have 15, negative 1, 7. So now I have a vector that's perpendicular to both of these. I got the first version from the cross product, but I reduced that just so the numbers are easier to work with. And we could really do any multiple. We could make them bigger. Again, we could multiply by 2. You could multiply by negative 1, by whatever you would like. And that's all this last note here is just saying that if we have two vectors u and v that are non-collinear just means that we have two vectors that are not pointing in the same direction. Okay, if they point in the exact same direction, the cross product wouldn't work. So they have to point in different directions. That's all this is saying. Then every vector that would be perpendicular to both of them is of this form. If I want a vector that's perpendicular to both of them, it must be some multiple of the cross product. So cross product will give us one vector that's perpendicular. Any multiple will give us the whole collection of vectors that would be perpendicular to those two vectors. A few properties like we did with dot product. As we see this time when we multiply, we actually don't get the same answer. We call that actually anti-commutative. That means that the cross product of A and B is the same as the negative cross product of B and A. Scalar multiplication still works, so I can distribute that scalar k to either of the two vectors and then do the cross product. So k times vector A cross B, or we can also put that k with the B as well. And our distributive property also works for cross product. We just have to be careful with order. Since u is on the outside, u has to come first as we do our distributive property here. So there's our distributive property. Lastly, a few examples here where we now can mix cross product and dot product together. Okay, so I have these three vectors. So if I do my order of operations here inside the brackets first, okay, means I have to cross A and B. So if I cross A and B, we will have 3, 1, negative 1, and we're going to cross that with B, 1, 0, and 2. Again, I'm going to take those first components and rewrite them, and I'm going to then start crossing. So I cover this up, and if I cross, I would get 2, subtract 0. For my second one, cover up the second spot and cross, I would have negative 1, subtract 6, gives me negative 7. And then cover up the last spot and cross, I would have 0, subtract 1, so I get negative 1. And now I want to cross that with vector c, so I'm just going to write the actual components in here. And now we need to do this all over again. So now I have to write out that I have 2, negative 7, negative 1, and I want to cross that with 2, 1, and 3. Rewrite those first two components. There they are. And if we start crossing, I'm going to have negative 21, subtract negative 1. That'll give us a negative 20. I'm going to have negative 2, subtract 6. And that'll give us a negative 8. And then cover up the last one. We're going to have 2, subtract negative 14. That'll be 16. So this is where we have to be careful again with our integer work. Be really careful. I'm not going to reduce this here. This is the answer that I got to the cross product, so I'm going to leave it. But if the question had asked for a vector that is perpendicular to both, then we could actually reduce that as well. In the second one, almost the same, except for here I'm going to now do the dot product instead as my second step. A cross B, at least we don't have to redo that. We've already done that here. So I knew that is 2, negative 7, negative 1. We're now going to do that dot product with C, so 2, 1, and 3. So this is where we have to remember now the dot product, okay, is going to be a scalar answer, a single number, and we do that by multiplying the corresponding components. So 2 times 2 is 4, plus negative 7 times 1. So I'm going to add on negative 7, plus negative 1 times 3 gives us negative 3. And if we add those together, we end up with our scalar here, -6. Sometimes here, because we end up with a vector answer by doing the cross product twice, we call this the triple vector product. This one, because we do cross product then a scalar multiplication or dot product, we end up with a scalar here, so we call this the triple scalar product. Lastly, this time I've switched it around and I've said let's do the dot product first. We have to be really careful. I'm actually not going to complete this question. I'm just going to think about, well, what would happen if we did this? So if I do this here, this would give me a scalar, and then I would be trying to do the cross product with a vector. However, to do cross product, I have to have vector crossed with another vector. So this calculation is actually not possible. So there is not possible. So there is no solution to this. Okay, so we actually have to watch our calculations to see what the results will be, to see if it's even possible. Here I can see that this would produce a vector crossed with another vector. The cross product would then produce another vector. Here, cross product would produce a vector. If I take a vector and I do the dot product with another vector, then I know that I'll end up with a scalar. But here our dot product would give us a scalar, which I cannot cross with another vector. Okay, we can't just change the operation. So this here then is not possible. So we end up here with no solution. Have a good day, guys. If you have any questions from the homework, again, please let me know, either through an email or we can set up some sort of conference for some extra help.